And if they do join in. So the first question, you have a triangular rod right here, and it's got a moment of inertia, it's got a lambda of this. So the density is changing as a function of x. And they want, using integral calculus, show the rotational inertia is equal to ml squared over 2. All right, so that's what they're asking us to do. And so what is I is essentially what they're asking us to find. So I is equal to the integral of r squared dm. But you got to remember that dm, we can change that because it's not the mass. Well, the mass is changing, but it's the distance that you're from some location that matters as well. And so dm we have to change to dr or dx. So the first thing I'm going to do is, because it's with respect to x, I'm going to rewrite this equation as x squared dm. Now the next thing is to figure out what this dm value is, because we're going to change the parameter. And so we have lambda is equal to the mass divided by the length, the total length from 0 to this would be that, which is also equal to dm over dx. And if we solve for dm, we get lambda dx. And so what we're going to do is we're going to replace the dm here with lambda dx. So we get the integral of lambda. Actually, let me rewrite it one more time. I'll put the x squared first, and then I'll put the dm, which is lambda as a function of x dx. And we evaluate this from 0 to L. Now you have to replace the lambda as a function of x with this equation right there. So substituting this for lambda, we can pull out the 2m over L squared. And we evaluate it from 0 to L of x squared, and then this x becomes x cubed dx. And so that's equal to 2m over L squared. And then you have the integral of that, which is x to the 4th over 4, evaluated from 0 to L. And when you clean this up, you're going to get ml squared over 2. So all of this cleans up to become ml squared over 2. And that's what they were asking us to solve for. So integrating this and taking the limits of integration, you'll end up with that. Okay, so that was part A. Part B is asking us, we've got this wheel. We've got this wheel now, and it's got those spokes. So it's got this, this, and this. And each one of these is what we just solved for, is little ml squared. So they want to know what the total moment of inertia is. For part B, you have I total is equal to I of the spokes plus I of the hoop. So I, we'll call these little things rods, plus I of the hoop. So how many of these rods do we have? We have 3 of them. So you have 3 times I of the rod, which we already solved for over there. It was ml squared over 2, plus the moment of inertia of a hoop, which is equal to ml squared. And so adding this together, you're going to end up with 5 over 2 ml squared. So that's the total moment of inertia I of that system. Part C, they're asking us, now you're going to apply a force, F. You're going to apply a force tangent to this wheel. So we apply a force tangent to the wheel, and after some time, we want to know what the final speed is. So if you've got a wheel with these spokes and you hit it, it's going to spin, and it's going to spin faster and faster and faster. So what is the final speed? That's what the question is asking us to solve for. All right, so what do I want to erase? So I total was equal to 5 over 2 ml squared. And now we're on part C. You apply a force there. If you apply a force, you have a torque. And you are also changing its angular speed. There's a relationship between torque and angular speed, and it's given by this. An external torque is equal to the change in angular momentum over the change in time. Okay? And so what can we do with this? We can rewrite it like this. Torque times the change in time is equal to the change in angular momentum. And the change in angular momentum is going to equal I times W final squared minus W initial squared. The reason why I'm not writing I1 final and I2 final is because all I'm doing is spinning the wheel. I'm not changing its radius or shape or anything like that. So we have this is equal to this term. We started with a spinning speed of 0, so this term goes away. And this I is really I total, so I'll write it as IT. And so now what we have is an equation for W final. We can divide both sides by I total, and we get W final squared is equal to the torque multiplied by the change in time divided by I total. Okay, and so the other thing we need to know now is that torque is equal to force times the distance. So the torque you're applying is this force right here, and the distance is a distance L. So torque is the applied force, or I guess we could say L times the applied force. You're this far away and you're hitting it that way. So that's what torque is equal to. We also know what I is equal to. I is equal to 5 over 2 ml squared. So what we end up with is W final is equal to torque, which is L times F. So L times F times delta T divided by I total, which is 5 over 2 ml squared. One of the L's will cancel out in the bottom, and you end up with 2 F delta T, all divided by the 5, stays there, ml. And so that is the final speed. We just have to square root it, I believe. This was squared. So if I want the final speed, I have to take the square root of that. So square rooting this, square rooting that, square rooting that will give me W final. So that's what they're looking for in that question right there. So how many questions is the AP? Okay, so I'm just looking at Rio's question really quickly. I believe, according to Mr. Alani, he told me that there's going to be 2, and I think that's what it is. There might be 2 free response questions. One is going to be a 25-minute question, and one's going to be a 15-minute question. I think that's what it was. Or it's like 20 and 15 or something like that. And one of them is going to be like a design a lab type question, and the other one is going to be explain and justify. So you might have derivations on there, but then you have to explain, like, okay, after you've derived this equation, what if you change the moment of inertia from a hoop to a disc? How would the answer? Okay, what would happen to this or that? So it'll be that type of questions. And another type of question you might see is going to be something that's going to be along the lines of, so a student theoretically calculated that the acceleration of some falling thing is this much, but the actual falling thing that they got was this much. What went wrong? And you have to explain in that sort of context as well. So you'll have to derive, and then you'll have to explain what happens to your theoretical values. So 2 questions. I'm going to go with that for now. It might be 3, but according to Lonnie, it was 2 questions, and it'll be 45 minutes long. Okay. Part D. So part D, you have the wheel going up an incline. So we got our wheel, and it's going up the incline. And what they want to know is the free body diagram for this. So the free body diagram, you would have a normal force going in that direction, perpendicular. You have the force of gravity going straight down. And then the force of friction. Now, which way do you think the force of friction is going to be? This is how I analyze the force of friction. This wheel is rotating, going as fast in the, I guess it would be the clockwise direction. So if the clockwise direction is slowing down, that means the acceleration has to be in the counterclockwise direction. And the only way you're going to get counterclockwise is if the force of friction is in this direction right there. So what will happen is the wheel is rotating this way, but it's rotating less and less and less. Okay, and that actually answers question D2. D2 says justify why these are where they are. Well, the normal force is always perpendicular to your surface. The force of gravity always points straight down or towards the center of the earth. And the force of friction, based off the reasons I just said, it's slowing down as it goes up the incline, which means that the force of friction has to be in the same direction as the angular acceleration, which is slowing down the object. Part E. They want to know how high, it looks like, they want to know how high this object will go up the incline. So for part E, we want to know this height right here, h. We're starting here, we're ending right there. We'll call this E1, and I'll call this E2, where E just stands for the conservation of energy. So the energy at the bottom is equal to the energy at the top. And so we can start writing down our energy equation. E1 equals E2. And so the energy at the bottom is all kinetic energy. So you're going to have kinetic energy initial rotational plus kinetic energy initial translational, and all of that is going to equal the energy at the top, which is mg times h. I should write UG final first. So that's the energy equations we're going to be using, and now we can start plugging things in. So kinetic energy rotational is 1/2 I omega squared plus the translational kinetic energy, which is 1/2 mv squared. And the m that we're talking about is the total mass. Remember, this thing has 3 of these plus the mass of the hoop, so I'll call it m total. And all of that is going to equal the energy potential at the top, which is mg, m total g, times h. And now we can start cleaning things up. We're asked to put everything in terms of I and omega. So we need to not have velocity terms here. So velocity is equal to omega times r. What r did we use here? We used L. So omega times L, where L is the distance from the center to one of these. Remember, the distance from the center to here is one distance of a spoke, which is L. So omega times R, or in this case, R is equal to L. And I is I total, which we've already solved for. And is there anything else? M total is equal to the 3 spokes mass plus the mass of the hoop. So M total is equal to 4 times big M. And so you can clean up now. You get 1/2 1/2 I total. I total was equal to ml squared. No, we just leave that alone. So 1/2 I total times omega squared plus 1/2 m total times v squared, which is omega times L squared. There we go. So I'm replacing the v with omega times L, and all of this is equal to m total times g times h. And you solve for h. So divide both sides by m total times gh, and then clean this up a little bit. What you'll end up with is h equaling omega squared 4ml squared plus I total, all divided by 8mg. Now, that's what you get final when you replace the m totals with 4m. So you'll clean this up, you'll replace m total with 4m, and then this is the result you'll get at the end. So that's the height at the very top. And these questions, they all have a pattern. We're just going to be using this conservation of energy nonsense here for each of them. Okay, so that was question 1. Question 2. Let me just make sure I've read question 2. So question 2, you've got a ball that's rolling down a table. And if you can do these questions after this, you should be able to do the homework questions too, because I made them very similar. So question 2, you've got a ball that's going to be rolling down. It's going to hit a flat part. And then from here, it's going to go some other distance right there. So it's going to go like that, and then fall down. And what they told us was this distance right here is 1 meter. They told us this angle right here is 30 degrees. And so what we could do is figure out what this height here is, h. H will equal opposite over hypotenuse, so that's sine theta. And so we end up with 1 sine theta. H equals 1 sine theta, or 30 degrees. And so H equals 1/2, or 0.5. Or the translational kinetic energy, they're asking you for the whole thing. Well, if we just look at this being 0 height right here, then as it falls, at the top we have potential energy, gravitational, initial, and it's going to equal kinetic energy total, final. There is no more height. We're going to assume this is y equals 0 right here. And so all you have to do to solve for this is just plug that in right there. So the total potential energy is equal to, so K total final at the end of this table right here is going to equal M times G times H, which was a half. And that's it. And that'll equal 2.45 joules. Okay, so that's what they were asking for. They were asking for the total kinetic energy. This energy is the combination of both kinetic and this is the combination of rotational plus translational. Okay, so for part B, they want to know what the final spin is right here. So how fast is this sphere spinning when it goes from here, when it wasn't spinning, to down here? And so we can use conservation of energy again, just like before. We know what this is now. It's 2.45 joules. So we can say that kinetic energy total at that point right here is equal to kinetic energy rotational plus kinetic energy translational. And so over here you have 2.45 joules, and that's equal to 1/2 I omega squared plus 1/2 mv squared. And what you can do is you could put v in terms of omega. V is equal to r times omega, so this gets replaced. Let me just get stupid light out of the way. There we go. Okay. And so I is the moment of inertia of a, I forget what the object was, but its moment of inertia is equal to mr squared over 2. So you have 1/2 mr squared divided by 2 times omega squared. So that's this term right here, plus 1/2 m. And instead of velocity squared, we're going to have r squared omega squared. And all of this is equal to 2.45 joules. And then the last thing you have to do is solve for, is there anything that comes up? No. All you have to do is solve for omega. And so working this out, you will get 25.6 radians per second. So from here, all is known except for the omegas. If you solve for omega, omega will equal 25.6 radians per second. Okay. The next part man, I have to start my own, what are they called? Markets? My YouTube shop. So that way I can afford a new board. What do you think? We should get 2 more boards. The next part of the question is asking you to compare the kinetic energy rotational at the floor over the total kinetic energy at the floor. So they want you to compare the rotational kinetic energy at the floor divided by this. Now, if you look here, as long as it's on an inclined surface, it's going to rotate. But then once it leaves the inclined surface, it's no longer going to pick up any more rotational speed. There's no friction here that's going to allow it to spin faster or slower. So what's going to happen is whatever the rotational kinetic energy here is, is still going to be the rotational kinetic energy at the bottom. There's no surface for it to rotate faster. And so the kinetic energy, we could say that the kinetic energy rotational at the floor is equal to the kinetic energy rotational when it left the table. And the kinetic energy when it left the table is equal to 1/2 times mr squared, well, 1/2 I omega squared, and that's going to equal 1/2 mr squared over 2 mr squared over 2 times omega squared. So that is this top part right here. Now, what about the kinetic energy at the bottom? Well, all you have to do is look at the potential energy, just like we did before. The height from here to here, plus the height from here to here, all of that height is going to transform into kinetic energy. So all we have to do is solve for the potential energy, and that's going to equal the total kinetic energy at the floor. And so the total kinetic energy at the floor is equal to the total potential energy. And that's equal to mg h plus big H, where big H is the distance from here to here, is what I'll call it. And we know what the height of the table is. So you just plug these in. This is equal to 1/2 mr squared over 2 omega squared divided by mg h plus big H. And when you work this out by plugging all the numbers, we know what this is. We know what all these numbers are now. It'll equal 0.13. And that's the ratio. How far will this ball hit the table? Is the next question. It's question D. So from here to here is D. They want to know how far it's going to go when it hits the bottom. And so we need to know what, this is just projectile motion. We just need to know what the x velocity is at this point right here. And then we can use the equation v x is equal to the distance that it's going to go divided by the time. And so time will equal vx times, not time, sorry, d. The distance that it's going to go is going to equal vx times time. Okay, so vx, we can get vx because we know what omega is at this point right here. So omega at the table right here was equal to, let me just 25.6. So this was 25.6 radians per second, and that's going to equal v divided by r. And so you just multiply r by omega, and you'll get the velocity in the x direction, because at this point right here, it's not moving up or down, it's only moving in the x direction. And so you get velocity is equal to omega times r. So we've got our velocity term. It's omega, or I guess we call it velocity x is equal to omega times r. And how do we get time? Well, it's just the distance it's falling down by. We can use the equation h, which, or delta y, is equal to v naught t plus 1/2 at squared, where it didn't have a y speed in the beginning, so that term goes to 0. And if we solve for time, it's going to equal 2h divided by g square rooted. So that's our time. And finally, we can plug both of these in. We can plug in this and this into our distance equation. So distance is going to equal omega times r. That's the v term multiplied by the t, which is 2h divided by g. And there's your distance, and it'll equal 1 meter. Okay. So the last part, this is an explain question. It's going to ask you things about explaining stuff. So this last question, let me just read it with you. Okay, part E. A sphere of the same mass and radius is now rolled down the inclined plane. The rotational inertia is equal to this. So before we had our hoop or cylinder, I believe it was a cylinder, the I cylinder was equal to mr squared over 2. And now we have a sphere whose moment of inertia is equal to 2/5 mr squared. Okay, so we're going from here to here, and they are asking, is the total kinetic energy of the sphere at the moment it reaches the floor greater than, less than, or equal to the energy of the cylinder? So they're asking us for the total energy. The total energy is the rotational plus the kinetic. That doesn't change because the total energy was dependent on the height. So it was the total energy at the bottom was just mg h, or mg little h plus big H. Nowhere in that equation was there moment of the sphere or moment of the cylinder. So the masses are the same. It doesn't matter. The mass, nothing will change here. The total kinetic energy won't change. Now, what will change is the amount of spin that you're going to get. So let's say, I don't know how I'm going to do this. This red pen represents your total energy. It's the total potential energy. The black is translational. The green is rotational. How much, and this is a cup we're representing, how much you allocate into here and here will depend on what the shape is. But the red pen, however much you started with, it doesn't matter. It's going to be the same value no matter what. It's when this thing changes to this, then the amount that you can pour into here versus here is going to be different. But together, they'll always have the same total energy. That's how you want to think about it. The next question. Is the rotational kinetic energy of the sphere at the moment it reaches the floor less than or equal to or greater than? Does it say greater than? Greater than, less than, or equal to the rotational kinetic energy of the cylinder. Okay. So for this one, the answer is let's see here. 2 questions on each of the 2 separate. Okay. So I cylinder, according to this equation, is going to be greater than I sphere. And so if this is true, then you're going to have less energy here, less rotational kinetic energy. So kinetic energy rotational of the sphere at the bottom will be less than the kinetic energy rotational of the cylinder. Now, that doesn't mean it's going to be spinning, this is going to be spinning slower than this one. What it's saying is that in order for you to turn this thing, you need to put in more work. This thing, you could think of eyes the same way as we think of mass. If there's an object that has more mass and you want it to go down, you have to do more work to it. And so it'll have a greater speed at the bottom, or greater kinetic energy at the bottom. With more mass, two objects, object A, object B. Object A has twice the mass of object B. When you let them go, they're both going to fall. They're both going to fall at the same speed, but this is going to have more kinetic energy at the bottom. Even though they have the same speeds, this one's going to have more kinetic energy translation at the bottom because it has more mass. Similarly, when we're talking about rotational stuff, because this has more rotational mass, it's going to give you more rotational kinetic energy. It just requires more from you to get this thing to spin in its rotating direction. Another way to think about it is in terms of its angular momentum. This one's going to have a greater angular momentum than that term right there. Okay. And then the last part is asking, is the horizontal distance traveled going to be different now? So when the cylinder fell off the table, it went some distance d. Will that change to have the power of YouTube? So when you see this a second time, it won't even be there. It'll be gone. So when you get to the bottom, before it's going to launch off the table, well, I guess I could have said it with that because it's going to have a greater omega speed. So at the bottom, a sphere, the velocity of a sphere will be greater than the velocity of a cylinder. And the reason for that is because the kinetic energy translational will be greater. So imagine this. You have 100 joules, and you have kinetic rotational plus kinetic translational. Translational is what this is about. So in part B, we said that because the one with the greater I is going to have more of this, which means it has to have fewer of this. So the one with the smaller amount of I is going to have less rotational. It's not going to rotate as much. It's not going to have rotational energy as much. And therefore, the remaining part of this 100 joules is going to go into the translational speed. And so if it has a greater translational speed, when it launches, it will go further because the time that it's falling is the same. And the only difference is the velocities when it launches with. And the velocity of the sphere, because it has more translational energy. Question 3. Hope it's an easy one. Of course it's not an easy one. So you've got a hoop-de-hoop, and they want you to draw a free body diagram for each of those points right there. Now, I can't tell you enough how many of you have lost points because you didn't do your free body diagram correctly. I'm looking at you. Oh, you didn't know YouTube has cameras the other way too? I can see what you're doing. And what I see is that you're playing on your phone. Get off your phone. Okay. Thank you. So the free body diagram. At A, we've got our loop-de-loop here. It's going to go like that. And then was it going to go out? Please don't tell me it's going to go out. Of course it's going to launch outwards. And it goes up like that. Woohoo! So this is point A. This is point B. And we want to draw free body diagrams. So at A, you have a normal force pushing this way. You have the force of gravity going down. And you have the force of friction pointing upwards. Otherwise, the ball wouldn't rotate. Okay, so what's happening is as the ball goes up A, if the force of friction is up, do I have a ball here? So as the ball is going upwards, right, it's spinning this way to go upwards, but the force of friction has to be going in the opposite direction from the spin in order for the ball's rotational speed to slow down. So as the ball spins upwards, like that, it's going to spin less and less and less. And the only way you're going to get it to spin less is if the force of friction is pointing upwards. All right. For B, it's just two forces going down. You have the normal force, and you also have the force of gravity. Okay. You could do it like this, or you could put them both right there at that point, pointing down. I think the AP would actually like you to do it, like 2 points going down from that. But I'm lazy. What is the minimum velocity required, or what is the velocity at A? What's the question here? Part B is derive an expression for the velocity at point A. Okay. So we start off at some height here, h. So we're going to have energy not in energy at A. And we just compare the two. The energy in the beginning is equal to the energy at A. The energy in the beginning is equal to mgh. The energy at A, it has three energies at A. It's got rotational, kinetic, translational, and potential because it's some height. So we have mg times big R plus 1/2 mv at A squared plus 1/2 I omega squared. And now we can replace omega with R. So I'm just bringing that to the other side, is equal to 1/2 mva squared plus 1/2 I. I is equal to 2/5 mr squared. Don't get confused. This little r is for the sphere. Big R is for the hoop radius. Okay. And the omega is velocity squared at A divided by R squared. So that's how fast the little ball or sphere is spinning. And so we can cancel out the masses. And our objective is to solve for VA. So what we end up with is VA. All you got to do is solve for VA now. Just bring all the other stuff to the other side. VA will equal square root of 10/7 G H minus R. And that's the velocity at A. Part B2. B2 is asking for the normal force at A. So the normal force at A you just have to use centripetal force equation. The centripetal force is equal to MAC, and so we have only the normal force acting in the centripetal direction equals MVA squared divided by big R. And we know what VA is from the last part, and you just substitute it in. So you end up with m over r times, well, let me clean it up a little nicer. You get 10 over 7 m g h minus r, and on the bottom you got nothing. So that's it. R, you have an R. Okay, so 10 mg h minus r over 7r. That's the normal force there. Part C. Part C is asking us, whoa. Calculate the ratio of rotational kinetic energy to the translational kinetic energy of the sphere at point A. Okay, so the ratio of the kinetic rotational divided by the translational at A. And so that's going to equal 1/2 I omega squared. And this is the translational, which is 1/2 mv at A squared. The 1/2s cancel out. And here you have 2/5 m little r squared multiplied by v squared over r squared. And down here you just have m va squared. The m's cancel out. The r squares cancel out. The VAs cancel out. And so the ratio is equal to 2 divided by 5. That's a terrible 5. That's a good 5. Okay. Next question. The next question is, the minimum release height h necessary for the sphere to travel around the loop and not lose contact with point B is h minimum. The sphere is really replaced with a hoop of the same mass and radius. Will h minimum decrease, increase, or so on? Okay, so the answer to that, this is question D, is it would. I don't think you can see that color. That's a terrible color. You're gone. Okay, so part D. The answer is increase. That's not how you spell increase. So if you go from a sphere to a hoop, you need to go at a higher height. Why is that? I of the hoop is greater than I of the sphere. And we just finished talking about this. The larger the hoop is, the smaller the kinetic energy translational is. So kinetic translational is less than the kinetic of the hoop, is less than the kinetic energy sphere translational. And if the kinetic energy is less, then the velocity is going to be less. Velocity hoop versus the velocity of the sphere. So when you get to point B, you're going to have a smaller velocity. And if you have a smaller velocity, it's not going to go fully around the circle. So in order to get a larger velocity, you need to go higher up and let it go. So if you let the hoop release from a higher height, then it will go because it'll have enough velocity to overcome the loop. Okay. And so the last part, I think, is the most annoying question of this. Is there another part to it? So what is the total height that this thing is going to go above? All right. So I gotta really draw this out here now. Let's turn it this way. I don't ever turn it that way. Now I know why I don't turn it that way. So you're going to start off at some height, h. You go around, and then you're going to release the object at this point right here. And the release height is r, same as here at point A. And so once it's released, it's going to be going with a velocity, we'll call it c, because this was the velocity at A, this was the velocity at B, and so on. Oh, I gotta move really close. So this is the velocity. When this thing launches, it's going to reach some height right here, h. Okay? So what we're going to do is we're going to treat it like a projectile from this point right here. It's going to go up some height. This height right here from here to here is going to be delta y. The height from here to here is going to be r. Okay? So if we know what the velocity at c is, we can take the y component of it and do the rest of the things that we need to do. So what's the velocity at c? Well, and the velocity here. Oh, this is so hard. Okay, so the velocity at the top in the y direction squared is equal to the velocity of c in the y direction squared plus 2a delta y. So what we're solving for is this height right here. Once we know what this height is, we can just add it to r to find the total height. The velocity at the top in the y direction is 0. So that term goes to 0. Now what's velocity c in the y direction? Well, we have 0 equals the velocity in the c in the y. This is the opposite side, not the adjacent. So we have vc cosine, not cosine, sine, theta all squared. So that's this term in terms of just vc. And that's going to equal 2 or negative 2 g delta y. Okay. And so we can solve for delta y. Delta y is going to equal vc squared sine theta squared divided by 2g. So we've solved for delta y here. And then from that, you can remember that the velocity here and the velocity here are going to be exactly the same. The height at C and the height at A are exactly the same. So what we can say is the velocity at C is equal to the velocity at A, and we know what the velocity at A is equal to. The velocity at A was equal to square root of 10 over 7 g h minus big R. So plugging that in for VC, we get delta y equals 10 over 7 g h minus R sine squared theta divided by 2g. The g's cancel out. And We just clean it up a little bit more. Delta y, well, I'll do that at the end. So this is what delta y is equal to. And so the total height, y total, is equal to delta y plus r. And so that's going to equal this stuff cleaned up, which will be 5 h minus r sine squared theta divided by 7. So that's delta y, and you just add to it r. And this is the total height. Okay? Now, is there another way you could do this? Can somebody write down what other way we could have gotten the total height? Just write down what other method we could have used. You don't have to say the entire method, just tell me what method we could use. Anybody, write it down in the comment section. Here we're using kinematics to solve for it. Are people still on? I can't tell. Give me one thing. Come on, come on, come on. Energy is correct. You would have to use conservation of energy. So what you could do is figure out what the energy at the bottom here is, or something like that, the energy at this point right here, which is H. And then you could figure out what the energy at the top is. Now remember, the energy at the top is not the same as the energy at this height right here. The height here is not going to be the same as the height here, because over here, there's no rotational energy. Over here, there's going to be rotational spin. So what you would write is the energy at the top right here, which is mgh. And over here, you would write mgh prime. That's what we're trying to solve for. Plus, it's got kinetic energy, 1/2 mv squared at the top, plus 1/2 I omega squared. Now, it's got no y velocity, but it still has an x velocity here. So this term isn't 0 at the top. There is a velocity in the x direction. So you have a translational energy plus a rotational energy. And then from here, you can solve for h prime. So you just bring all of these things to the other side, and you end up with h prime equaling mg h minus 1/2 mv at the top squared minus 1/2. If you want to solve it in terms of w or I, whatever, that's up to you. Omega at the top squared, all divided by mg. So that's the other way you could have solved this question here, by using just energy before, energy at the bottom. And the other way was using kinematics. So both of those are true. And so before I let you go, I just have one question. If I were to change the, what was this, a sphere? If I change the sphere to a hoop, would it go the same height or would it go a smaller height? So this was the final height with a sphere. If I changed it to a hoop, would it go just as high when it goes to the apex right there, or will it go at a lower height? Well, everybody else died off. Well, that happens. So I'll leave that to you to answer, and then I'll get back to you tomorrow if you want to think about it. If I were to change this from a sphere, which we were using, to a hoop, would it be the same height or lesser height? And I refer you to go back to the question I did before. So go back and watch this. Real, you fell asleep for a couple minutes. We're back to school now. You got to learn. So takes more energy to reach the same velocity as a sphere would, so probably less. Sean, that is correct. That is exactly what it is. So if we change this to something with more moment of inertia, then it won't go as high up. So just keep that in mind when you're doing these kinds of questions. Ask yourself like extra questions like, well, if I were to change this, because that's probably what the AP is going to do. And then also another thing you can think about is if you were to design an experiment to find the moment of inertia, like